Welcome to the another lecture of electronic devices. In this lecture, we are going to cover resistivity and the seed resistance. So, what is resistivity? The resistivity is defined as the measure of resistive power of a specified material to the flow of an electric current. Resistivity is commonly represented by the Greek letter rho. The SI units of electrical resistivity is in ohm meter. So resistivity is defined for a particular resistor R with area A and length L, that is rho equal to Ra by L. So if we talk about material superconductors which is having zero resistivity in ohm meter, on metal the resistivity is about of 10 to the minus 8. Semiconductor the resistivity is depend on the temperature. For electrolyte it is also variable and depending on the temperature and the applied voltage. For insulator it is around of 10 to the power 16 ohm meter. For superinsulator the resistivity is of around infinite. So how the resistivity is measured? Resistivity can be measured through two probe point method, 4-point probe method. So if we talk about 2-point probe method, it is basically calculated using on a 2-point contact. So each contact serves as a current and as a voltage probe. So appear to be easier, but interpretation of measured data is difficult due to various resistance inclusion. So as we are seeing in this figure, so design under test, this resistance is having the contact resistance and its own resistance RDUT and the wire resistance. Another method of measuring is 4-point probe method. In this method, which is originally proposed by Wiener to measure the resistivity of the earth through magnetic method. Later it is adopted for the semiconductor vapor as well as widely used in vapor manufacturing industries. In this particular diagram, you can see that in 4-point probe method, two poles or 2 points are used for measuring current and two ports are measuring for voltage. So why we are using 4-point probe method is to attain the standardization of probe technique with better accuracy. Another point is that current path is the same as that of 2 probe method, but the voltage is measured with two additional contacts. So this is the main advantage of this 4-point method, and the voltage drop across the RW and RC are negligibly small, so can be neglected, and the major voltage is essentially the voltage drop across the design under test. So this is the measuring procedure of the 4-point method as shown in this figure. It is having four equally spaced inline probes with probe tip diameter is small compared to the probe spacing. So this is N-type and this is P-type material. So in which N-type material is having the particular thickness T and the depletion region acts as an insulator in this particular NP type resistor. So the current is the most commonly passed between the outer two probes and the voltage difference is measured between the two inner probes. The resistivity is in 4-point probe measurement is given by rho equal to 2 pi s f dot v upon I, where s is the distance between two probes. F represents the correction factor, where f is given by f1 multiplied by f2 and f, where f1 corrects for sample thickness, f2 for literal sample dimensions, f3 for placement of the probe relative to the sample edges. So another resistance is seed resistance, which is a measure of resistivity averaged over the surface. So the seed resistance is measured for the resistance of thin film that are normally uniform in the thickness. The utility of the seed resistance as opposed to the resistance or resistivity is that it is directly measured using a 4-point probe measurement or indirectly by using non-contact eddy current based testing devices. The seed resistance can be used to compare electrical properties of devices that are significantly different in sizes. So from this figure, it is the diagram of a particular material which is having a W width, L length and P thickness. So R is given by R equal to RSH L upon W, where RSH is a seed resistance. In another way, we can represent R equal to rho L by A, where A can be represented by W into T, and totally you can see that rho upon T is equivalently with RSH, which is given by seed resistance. So L upon W has known unit and rho upon T has unit of ohms, but the rho upon T is not the sample resistance. To distinguish between R and rho upon T, often practice surface resistance given in units of ohm per square. So seed resistance is applicable as long as the measurement is related to a square. So if we talk about a bulk sample where T is very greater than S is the probe spacing. So a spherical current from the outer probe tips is assumed. So differential resistance is given by delta R equal to rho dx upon A, where rho is the resistivity, dx is the differential length, and A is the surface area penetrated by the current from one probe. So to determine the resistance between the voltage measurement tips, one integrates between x1 and x2. So R is given by integration of x1 to x2 rho dx upon 2 pi x square, where 2 pi x square is the area of particular sample. So through calculation we can calculate that R is given by 1 upon twice as rho upon 2 pi. So from this particular equation we can get rho equal to 2 pi s into V upon I, as the superposition of the current at outer two tips leads to R equal to V upon 2I. So if we talk about thin sheet where thickness T is very less than S, so we can have the case of current rings so that A equal to 2 pi xt. So R can be calculated as rho equal to 2 pi T log of 2. So as before, superposition of current at the outer two tips leads to R equal to V upon 2I, so that the resistivity for a thick film sampled as rho equal to pi T upon log of 2 into V upon I. The expression is not dependent on S. So sheet resistivity is defined as R is equal to rho upon T K V upon I, where K is the geometric vector, which is for a semi-finite thin film is pi upon log of 2 equal to 4.53. So through this we can calculate the sheet resistance of a particular thin sheet material. Thank you.